A spherical pill with volume V and surface area S is swallowed and slowly dissolves in the stomach, releasing an active component. In one model it is assumed that the capsule dissolves in the stomach acids, such that the rate of change in volume, dV/dt, is directly proportional to the pill's surface area. So we will first show that the rate of change of volume with respect to time is minus k times v to the power of 2/3, where k is a positive constant. Now the volume of a sphere is 4/3 pi r cubed. The surface area of a sphere is 4 pi r squared. We can get S in terms of V by writing R in terms of V in this first equation. So we multiply by 3 over 4 pi. Multiply both sides by 3 over 4 pi here, and take the cubed root, which is the same as raising 3v over 4 pi to the power of a third. Next we plug this into R for the surface area. So here's the surface area. We plug 3v over 4 pi to the power of a third in for R, and we have to square this. So we just multiply these powers. So we get 2/3 here. Okay, so we raise everything inside the brackets here to the power of 2/3. So we'll have v to the power of 2/3. We leave that to one side. And then we have just all this stuff here, which is just a number, it's just a constant. We can call that constant k. It turns out to be 36 pi to the power of 1/3. Now we're given that dV/dt is directly proportional to the surface area, which is given by kv to the power of 2/3. Now it's important to realize that k is a positive constant. This number is positive. dV/dt is negative because the volume of the pill is decreasing. See, dt is always a positive quantity. That's the change in the time. That's a later time minus an earlier time, if you like, over an infinitely small interval of time. Since time is always increasing, a later time minus an earlier time has to be positive. But the change in v is going to be negative, because the later volume minus the earlier volume is negative. The later volume is less than the earlier volume. Of course, we're dealing with infinitesimal intervals here. Anyway, so dv is negative, dt is always positive, since we assume time is always increasing. It means that this derivative is negative. Now we are given that dV/dt is proportional to the surface area. That means if we double the magnitude of the surface area, we will double the magnitude of dV/dt. So that means that dV/dt is equal to a constant times this. So if we were to call the constant c, to be ck v to the power of 2/3. But since k we know is a constant from the previous part, it was whatever, 36 pi roughly to the power of a third, I think. Well, this is just a constant, and we can just still call it k, but of course it's a different k from this k up here. But it doesn't matter what we call it. We're not interested in the actual number that we got in the previous part. So we can just call it k, but we have to make it negative. K has to be negative because dV/dt is negative, and v to the power of 2/3 is positive. So we could either write down the equation like this and just state that k is negative, or we could make k positive and put a minus sign in front here. But then we have to emphasize that k is positive. And that's what's actually done here. The constant here is assumed to be positive. Now we're going to solve that differential equation subject to this initial condition. We are going to call the volume of the pill at time 0, that's the initial volume of the pill, v sub 0. So we just separate the variables here. So we divide across by v to the power of 2/3 and multiply both sides by dt. And then we just integrate both sides. So on the left hand side we're integrating v to the power of minus 2/3 with respect to v. And if we integrate minus k with respect to t, we just get minus k times t, since minus k is just a constant. And we have the constant of integration, and that comes from the left hand side as well, of course. Okay, integrating this, we add 1 onto the power. Minus 2/3 plus 1 is 1/3. and we divide by the new power, so we divide by 1/3, but that's the same as multiplying by 3. So we divide both sides by 3 and raise both sides to the power of 3. Next we apply our initial condition. So if we plug 0 in for t, v is v0. So plug 0 in for t, we get c over 3 cubed. So we take the cubed root of both sides, or raise both sides to the power of 1/3, and then multiply both sides by 3. So we get 3v0 to the power of 1/3. So finally we can write down the particular solution. So for c we have 3v0 to the power of 1/3. I'll write c first. Minus kt second. It's divided by 3 and all raised to the power of 3. We can then divide each of these terms by 3, so we'll end up getting our solution as seen here. Now in part B of the question we are given that half the volume has dissolved after 3 hours. So the initial volume is V0, so that means we want V to be half the initial volume. So V is decreasing with time, of course, and it decreases from an initial value of V0 to half its volume, V0 over T, in a certain amount of time that we've defined. So we put V0 over T equal to this expression here and solve for T. Well, actually we are given T. At T equals 3, V decreases from V0 to V0 over 2. So we just plug 3 in for T, the 3's cancel, so we get V0 to 1/3 minus K, and that's raised to the power of 3. We're looking for K, so we need to then raise both sides to the power of 1/3 to get rid of this power of 3. So we'll have V0 over 2 to the power of 1/3 on the left hand side. And we can write K like this. We can factorize V0 to the power of 1/3 out of this. So we're going to get 1 for this term. And for this term here, we're going to get minus 1 over 2 to the power of 1/3. Well, that's the same as 1 minus a half to the power of 1/3, because 1 to the power of 1/3 is just 1. In part C, we want to estimate the time required for 95% of the pill to dissolve. So here's the solution to the differential equation with the value, or the expression for K worked out, plugged in. So just plug in for K here. So we want the volume of the pill to go from the initial value V0, whatever that is, to 5% of this initial value. So when the volume is 0.05 V0, then 95% of the pill has dissolved. So we've plugged that in for V. Okay, now we can factorize V0 to the power of 1/3 out of the right hand side. So if we take it outside, we still have to raise it to the power of 3. Well, V0 to the power of 1/3 to the power of 3 is just V0 to the power of 1. So that can come out, so we're just left with 1s in place of those V0s. Remember now that 1 minus 0.5 to the power of 1/3 is all multiplied by T over 3, so we can't cancel those 1s obviously. Anyway, we replace V with 0.05 V0 and we can cancel off the V0, so it doesn't matter what the initial volume of the pill is. We'll get the same value for the time taken for 95% of it to dissolve. So we need to subtract 1 from both sides, so we get 0.05 to the 3rd minus 1. Then change the sign, so we get 1 minus 0.05 to the 3rd equals 1 minus 0.05 to the 3rd to the power of T over 3. Well, it's actually 1 minus 0.5 here, so we will be dividing 1 minus 0.05 to the 3rd by 1 minus 0.5 to the 3rd, and then that gives us T over 3, so then we multiply by 3 to get T. That works out to 9.15 hours. Suppose we want to find out how long it takes for complete dissolution of the pill, for the pill to dissolve completely. Well, in that case we want v to equal 0. So we put 0 equal to all of this. Now the only way this can be 0 is if the thing inside the square brackets is 0, because obviously v0 is not 0. So we're just setting all of this here equal to 0, and we add 1 to both sides of this, or sorry, subtract 1, so we get minus 1 on the right hand side, and then we divide across by 1 minus 0.5 to the power of a third. And if you calculate this and multiply it by 3, you get 14.54.